Professor Efrat Timsoni from Bar-Ilan University, Israel, to be among us. So this is as many of you know, this is a part of the Spark project where from this side, myself, Professor Rahul Martin, Professor Rohit Narula were the investigators, and from the Israel side, it was originally Professor Asaf Elbach and Professor Efrat Timsoni and Professor Dan Kozinski. They were the partner investigator from the Israel side. But Professor Asaf Elbach, we know that unfortunately he left us in February. This was just before he was planning to visit India and again giving a series of lectures. So one of the very important part of this Spark project is that you invite your collaborators from abroad, and then you arrange a set of lectures which will be attended by the students, postdocs, and these lectures will be also video recorded, and we have to deposit this video with the Spark authority, and we are hoping to put all these things in a more consolidated way at some point of time. But fortunately enough, in IIT Delhi, we have a very good video recording facility thanks to the ETSC. So before that we put it in the YouTube or something like that, so that for wider circulations. But more importantly, it was a great opportunity that Professor Efrat Timsoni, with work in the field of strongly correlated electron systems, quantum Hall systems, superconductivity, and various other similar type of systems is very well known. She readily agreed to give this series of lectures on a topic which is very close to her heart, quantum Hall systems, and that too in graphene. I think mono and multi-layer graphene system. Now, about Professor Timsoni, of course, she's much senior to me. I was a postdoc with her for the last period of my postdoc in Israel. So, but I need to, because of the formality, I have to introduce her. And so she did her PhD from Weizmann Institute, and then she was in University of Illinois on a Champaign as a postdoc, and then she came back to Israel, and in 2008 she joined. Before that, she was in Haifa University, and in 2008 she joined the Bar-Ilan University, where she is now one of the senior members in the physics department. And I learned many things, means even the initial part of my postdoc, I really didn't work with her. But whenever I knew her, because she came first, I think, in India in 1999 in a Indo-Israel conference, and that was the time when I met with her. So whenever I have some queries regarding quantum Hall systems, I used to go to her, and she was an amazing teacher, and she used to explain in it. Like, I remember she explained to me Choker-Coddington model at one point of time, even though I didn't know anything about the renormalization group, but she explained it so nicely on a board which was adjacent to the room. So I hope that you are going to learn a lot. So make sure that you keep this particular event quite seriously. So those who are coming today, unlike our classes where the percentage of the attendance drops over the time, that should not happen. You are going to really get something very solid out of this particular series of lectures, and it will be beneficial for you. So because particularly the lectures, because when you are going to put this video recording, we do not know, right? So therefore, and you have an ample opportunity to interact with her. I think they can ask questions in between.
Absolutely. I was going to say, stop me in the middle. Anything,
And small warning that your question will also be video recorded, but this is good for your publicity, so you must appreciate that particular opportunity, right? And please switch off your mobile phone during the lecture, because otherwise they told that you will interfere with the recording, right? So please do that. So with that brief introduction, I invite Professor Timsoni to
Thank you very much. So first of all, I really thank Sankalpa for inviting me and for such efforts to host me very, very nicely. And I also want to mention that I now just started a post as head of the department. And one of the things that we have in our department in Bar Ilan, we encourage students from abroad, and we have a growing Indian community in campus. We're doing postdocs and also a few graduate students from India. So I just want to advertise that, I have a long history of supporting collaboration between India and Israel, and I want this to continue and hope to see some of you visiting and maybe coming for doing research. Okay, so let me now go straight to the story, and today is really an introductory lecture. I will start from very basic. Maybe for some of you it will be too basic, but I think it's never bad to have something too basic, to have profound foundations to build on the more complicated stuff. Eventually, towards the end of the lecture series, I'll tell you about more recent research of quantum Hall effect in graphene devices and on my own work as part of it. But today I'll just start from the quantum Hall effect, which I'm sure many of you heard about. I'll introduce the basic foundations, and we'll see that we're going to use them throughout when we get to graphene. We'll build on that. And as Sankalpa also said, please don't hesitate to ask questions in the middle. I'm coming from a culture where, you're smiling. Lectures are very interactive. Students are very bold. I'm used to that. I like students who are responding. And so please don't hesitate. And you can also ask me questions later if there's no time. So don't worry. Okay, so let me start the story. So the quantum Hall effect, I think, is probably the first observation in experiment of a phenomena that later on we call, in the more general term, topological phenomena or topological materials. And I think it was the first time that in a solid state material, in a very mundane material, just a piece of dirty silicon, you observe a phenomena by measurements of electronic circuitry that reflects a mathematical object, a number, a topological index. This is the first example of a topological index that we'll discuss, and that's a fancy mathematics, but the fact that you can observe it very accurately in a solid state real experiment, I think it's amazing. And indeed, the first observation that I now just review won a Nobel Prize. In fact, 2 Nobel Prizes. The first was to von Klitzing on the integer effect. I'll of course explain all these concepts, and then a few years later there was the fractional effect was observed, and I'll try to convey the notion that they're all on the same footing. All these observations are coming from the same kind of physics. So what was the seminal experiment that started all this? In the early 1980s, von Klitzing and collaborators looked at a silicon MOSFET. It's kind of a transistor. Well, it has the property that by applying electric gates, you can confine the electrons to live in 2 dimensions. Okay, now of course the system is three-dimensional, but you know, if you trap a quantum particle in one direction in a single quantum state, effectively it behaves as if its motion in the, let's say, the z direction is completely frozen, and therefore it's two-dimensional. It has a two-dimensional kinematics, and then what he measured was the Hall effect. The Hall effect was the classical Hall effect, okay, was discovered by Edwin Hall 100 years before, in the 19th century. And it's the following. So this is something that is really elementary undergraduate physics. You take a piece of material and you apply current, electric current. So this is there's some source that passes current I, and of course now you can connect voltmeters to the system, and you know there is the Ohm's law. So if I connect a voltmeter between these two electrodes that that you see in the picture, what will I see? I see I mean, if it's just a regular metal or conductor, you'll see some ratio between voltage and current, and this is what we call resistance, right? Electric resistance. Now, if I put my electrodes, so let me draw here two, sorry, yeah, so this is one voltmeter, but I can also connect a voltmeter in the perpendicular direction across. Okay, so let's call this Vy, and this will be Vx. Okay, and if I'm passing current in the direction that you see in this picture, which is, this is the direction of the current, what will I see on the Vy? Will I see a voltage in the longitudinal, in the perpendicular direction? Any idea? Well, so if there is no magnetic field, sorry? So if there is no magnetic field, of course, I will only measure voltage in the longitudinal direction. However, now we put a magnetic field perpendicular to the conductor, this piece of conductor, and in the presence of a magnetic field, a voltage develops both in the longitudinal and in the transverse direction. What is the origin of this effect? It's just the classical effect that was discovered by Hall. It comes from basically a Lorentz force that is applied on electrons when they go through a magnetic field. Okay, so the magnetic field curves their path into creating some voltage in the y direction. So that's an old effect. Now, the experiment of von Klitzing and collaborators was exactly that experiment, but with a few new features in the system. First of all, as I mentioned, it's a two-dimensional system. So the electronic, it's not just a piece of metal, a metal slab, it's really a single, think of it as a two-dimensional system, and that turns out to be crucial. The second important thing is that he was looking at strong magnetic fields of Teslas, which are relatively strong, and low temperatures. Low temperatures approaching a few Kelvin, okay? So much below room temperature. And what he saw was a deviation from the classical effect, and let me just plot schematically the, sorry. So I'm plotting an axis. Okay. So let me first introduce two quantities. One is a Hall resistance, Rxy, which is the ratio between voltage in the y direction and current in the x direction. And the other is just the usual ohmic resistance, which is voltage divided by current in the same direction. Okay, these are just definitions, what I wrote here. And in a regular conductor, classical piece of metal, what you see is that Rxx has a relatively weak dependence on magnetic field, but Rxy will be zero at zero magnetic field. And if you look at it as a function of magnetic field, what you expect to observe is a straight line, okay? So what I'm plotting now is the classical Hall effect. And it's a straight line, and the expression for it is actually, this expression for the slope is very simple. It only depends on the density of electrons up to universal constants. So let me write it down. This is approximately given by a linear function of B divided by the density of electrons. And there are some fundamental constants here. I'm using units of CGS, so it's electric charge of the electron and the velocity of light. Okay, so this is the classical Hall effect. Everybody knows it, I hope, right? Okay, what was different in von Klitzing's experiment? What he saw was that, sorry, instead of seeing such a straight line, he saw that the Hall resistance breaks into plateaus. Okay, I'm trying to plot them not very nicely, okay? And it turns out that these plateaus appear at some discrete set of magic numbers. Okay, so what is the general expression for them was some universal unit of resistance. Okay, notice that Rxy has units of resistance, right? It's voltage divided by current, and there is some combination of the Planck constant divided by the square of the electric charge. That quantity has units of resistance. It's a basic quantum resistance, and these plateaus appear in special values of this quantity where you multiply it by a number, a prefactor, where this number, magic number nu, is an integer. So this is the integer okay. So all these plateaus appear at some, when the Rxy takes these special values. And where is this number coming from? If you look at the center of the plateau, you see that it relates to some special value of the magnetic field, where the number nu is in fact a ratio between the density of electrons, the magnetic field, and multiplied by a quantity phi naught that is the so-called flux quantum. So let me first write here a definition. What is a flux quantum? It's a fundamental combination of, sorry, maybe it didn't look very nicely. Okay, it's a fundamental combination of the fundamental constant, Planck constant, velocity of light, and E, which has units of flux, and that's what appears in the quantum mechanical phase of a wave function when a particle goes around a circle. We'll go back to this actually soon, but that's what it is. And what I wrote here, this expression for nu is a dimensionless number, okay? In fact, you see that what appears there, so phi naught is some constant, but NE over B is some very special fine-tuned ratio between the number of electrons and the number of, and the magnetic field, where magnetic field is actually a density of flux, okay? So there is some very magic connection between the number of particles and the number of flux quanta in the system. And this factor is therefore also called a filling factor, for a reason that will become clear soon, but also you can think of it as some kind of magic ratio between two entities, the density of particles and the density of flux quanta, and for some reason the system likes to be in these ratios, okay? So this is the integer effect, and later on Tsui, Stormer, and Gossard so exactly the same behavior, same qualitative behavior, but with fractional values of this magic number nu, and these fractions are, I'm writing here just examples, but you see they are all rational fractions that have a very special property, that they have a denominator that is an odd integer, okay, and that's important. So that is called this is called the fractional quantum Hall effect. Okay. So that's one observation is just that you see plateaus in the Hall resistance. But there is another even more astonishing thing. or maybe not more astonishing, but it's of course related. If you look at RxX, so RxX is just the usual ohmic resistance in the longitudinal direction. You see that every time there is a plateau in RxY, RxX becomes almost vanishing. So roughly RxX looks like that. I'm plotting it very schematically. Okay, there are some sharp peaks at the transition between plateaus, but otherwise, every time there is a plateau in RxY, RxX is nearly zero. Okay, so why is this astonishing? Because we're not talking about superconductivity, which I'm sure you all heard about. It's really current passing with no voltage, but this is a dirty piece of silicon, okay? So it's actually a very bad conductor. But nevertheless, when it is in this special state, special phase of matter, it behaves like there is no dissipation, there's no resistance, okay? And it looks like these two phenomena go together, the behavior of plateaus in RxY and the zero resistance, okay? So this is what I plot in red is RxX. Okay, so that's the effect, and soon enough there came some theory that explains it. To understand it, we can start actually from something very simple and very basic, but it still doesn't explain the effect, but of course it's important to do it first, okay? So, any questions, by the way, so far? Yeah?
So these fractions that you are observing, they are with the integers, like the nu has integer and fractional, or
so first of all, the way it appears here is just a definition, okay? So
what I'm asking is, so in the same experiment you are observing once nu as integers.
Okay, so if you look at clean enough samples, like the ones the samples in which the fractional effect was observed are just cleaner. They're also a two-dimensional electron gas, but they are in they were in gallium arsenide, so there are different kind of devices. And of course you see also the integer. You see the integer, but you also see a fractional, and the cleaner you go, you see more and more fractions. And the fractions are, they have some special hierarchy of states, okay? And I'm hinting again, the basic numbers are such that they're rational with an odd denominator, mostly. Okay?
So both of them exist?
Both of them exist in the same material. Okay. It's just a question of going to low enough temperatures, cleaner samples. Okay. But in principle, yeah. Okay? So, yeah.
In general, the relation, yeah. In general, you have whatever current and electric field applied, there could be, in general, you would expect the coefficient to be a tensor.
Yeah,
is there a reason that without magnetic field you never see the other thing, the off diagonal thing?
Oh yeah, there's symmetry, right? Time reversal symmetry. So
it follows from time reversal.
Time reversal symmetry, right? Yeah.
I see. So magnetic field breaks that, and that's why.
Yeah, that's exactly right. Yeah.
Is there a way of thinking about it rather than time reversal as parity? For example, B also breaks parity. Does it have nothing to do with parity?
Actually, that's we'll come to that in graphene.
Okay.
So because in graphene you can also change the carrier from electrons to holes, right? So I'm jumping ahead. But if you have a magnetic field, but you have particle-hole symmetry, once again it will be zero.
I see.
Okay.
I see.
So yeah, it's both parity and it's particle-hole and time reversal symmetry. Okay.
I see. Okay. Good.
Yeah.
Is there any relation between two integers? There will be so many fractions, or in principle,
no. So
any fraction can occur.
There is a sequence of fractions which favor these states.
Okay.
Okay. In practice, however, what happens is that each of these fractions is a different state of matter. It's a different phase. And sometimes it competes with something else, and therefore you don't see it in certain systems, and you do see it in others. Okay? But let's not jump ahead. But the important thing is that there is a sequence which at least has the potential of developing these special states. Okay? And there are really special states of matter. In fact, the transition between the plateaus is so you see there are plateaus, but in between you're jumping from one plateau to another. That's a phase transition. It's really a critical phenomenon. Okay. So let's first, in order to understand what's going on, the first thing we have to do is to look at the basic ingredient is a two-dimensional electron gas. And let's be very simplified and assume that it's ideal system. So just a free electron gas, just kinetic energy. I'm neglecting for the time being any potential energy, but we'll see that we will bring it back. And what it will do, it will play a very interesting role. But we just have a free electron gas in two dimensions in a magnetic field. Okay, so that's a simple quantum mechanics problem for undergraduate. I can write a Hamiltonian, and the Hamiltonian looks like this. It's just 1 over 2m okay, and that's square. Okay, that's what have I done here? I took the Hamiltonian of a free electron gas, kinetic energy, and the way to introduce the magnetic field is by introducing a correction to the momentum operator via vector potential. Okay, this I hope is familiar. And now in our problem, we have a magnetic field in the direction that is perpendicular to the system. So while the momentum, let's say, is in the xy plane, okay? And that's, of course, a momentum operator. Let me just remind. Okay, so momentum operator in quantum mechanics. Now, the magnetic field is in the z direction. So we can write a vector potential that enforces it. How will it look like? It has to be something whose curl is a magnetic, constant magnetic field, and we have the freedom of choosing a gauge, right? You remember there is a gauge freedom. So we'll choose a gauge that is called the Landau gauge, which is the following. I'm assuming that A is in the x direction, but it's linearly dependent on y. Okay? I could, of course, exchange x and y. Anything that is physically observable will not depend on the gauge choice. So we just choose it for convenience. Okay? Now let's see what we get from this. Sorry. All right, so okay, so now what you see is because the momentum in the x direction commutes with the Hamiltonian, right? Because the vector potential depends only on the coordinate y. We have a good quantum number, which is momentum in the x direction, but in the y direction we have an effective potential. Okay, so let me just go through it very I don't go through the details, of course, but if I look for a solution for the Schrödinger equation of this Hamiltonian, it turns out you can easily convince yourself that the wave functions can be written as, and let me introduce here two indices, which I'll explain in a minute. The wave functions are going to have this form. It's a free wave in the x direction, multiplied by some function of y. And here I'm just putting here indices because I claim that there are going to be two quantum numbers that come in. And this is going to be a guess, okay? I'm just making a guess on the wave function. If I plug it into this Hamiltonian, I find that this exponential factor will simply cancel, and we get an effective Schrödinger equation only for the function phi. And what is this effective Hamiltonian? It's now a one-dimensional Hamiltonian, only in the y direction, and it looks like that, okay? It's kinetic energy in the y direction plus something that looks like, what is this potential? Anybody recognizes? Harmonic oscillator. Okay, it's basically a harmonic oscillator. And I introduced here two quantities that I have to define. The first of which is this, what is this omega c? Okay, omega c is a frequency. This is the so-called cyclotron frequency, describes the frequency of motion of a charged particle in a constant magnetic field. There's another quantity here that I denoted by yk. What is yk? It's a constant, okay? It's not a variable, it's just a constant, and it's given by the same k that appears as momentum in x direction appears also in the inside this potential. Is there a pointer, or somehow I can I don't know. Do you see when? No, you don't see the. Sorry.
Laser pointer?
Is there a laser pointer or something? Just to, yeah. So maybe I'll just show on the screen there. So yk is defined as k times some constant, which has units of length, and this is okay. This is the so-called magnetic length. It's a length scale that appears, that only depends on the magnetic field up to some universal constant. And what is the nature of the system? So in fact, we find that electrons in a perpendicular magnetic field in 2 dimensions behave like particles that in one direction they are just free waves, they have a well-defined momentum, but in the other perpendicular direction they observe an effective potential that is like a harmonic oscillator, but this harmonic oscillator is centered around a set of positions, yk, here is a coordinate in the y direction, that around which the wave function is localized, and they are called guiding centers. Okay, so that's just a solution of a quantum mechanical problem, and let's see what we get from it. So the first thing, it allows us to solve very easily for the spectrum. What is going to be the spectrum? Notice that the spectrum, we have here 2 quantum numbers. One quantum number I called k, which has the significance of momentum in a single direction. The other quantum number I still didn't introduce is going to be quantized in integer values, and we get energies. This is the energy spectrum. It's going to be just a solution of a harmonic oscillator. So the spectrum is a discrete set of levels, and they are dictated by an index n. So let me plot them here. I'm plotting the spectrum as a function of k. Let's do it like this. It's 1, 2. Okay? And they follow this formula. They're equal spaced. Sorry. These are Landau levels, okay? They're so-called Landau levels. Okay, so this is a very simple spectrum. We all know the harmonic oscillator, and something I want you to notice is that, however, we have a 2-dimensional system, okay? We have 2 quantum numbers. Usually just a free electron gas has two momenta, right? Kx and ky, and the energy depends on both of them. Here, the energy does not depend on this k, okay? It's just a flat line as a function of k, okay? In fact, if you think of it as band structure, okay, in the language of band structure in solid state, it's a flat band, okay? It has many quantum states with the same energy, okay? And that's special to the 2-dimensionality of the system. So, and in fact, what is the role of the other quantum number k? It doesn't dictate the energy in any way. So what does it dictate? It dictates only the position around which the harmonic oscillator states will be confined. Okay, so schematically, if I want to plot how wave functions look, these functions that I call the phi of y, they're going to be, in fact, phi and k, they're going to be harmonic oscillator states centered around the guiding centers, and the guiding centers, as I said, they are related to the momentum in the perpendicular direction. So it's very strange. The wave functions are localized in one direction, but completely extended in the perpendicular one. For example, if I'm looking at the function 0, okay, so if I'm looking at it as a function of y, it will be just a Gaussian with a width that is dictated by the magnetic length LB. Okay, this is how it looks like. This is in the y direction. Okay, whereas in the x direction it's completely extended. It's just a free wave. And if I'm looking at our two-dimensional sample, we have a macroscopic system with some dimensions Ly and Lx. And so what are these guiding centers correspond to some positions in y. Let's say there is some particular yk, the wave function around it looks, if I'm plotting its magnitude, it will be spread out along the x direction, but it will be centered around yk with a characteristic width of order LB. Okay, that's how it looks like. If I look at another k will have, if I have this yk, okay, I have exactly the same wave function, but it's localized in a different location. And I can, if I now think of how many electrons can I put in my system, I see that there is a huge degeneracy, right? Because in fact, you know, if the system was infinite, the number of values of different k would be infinite, right? It's a continuum of states. But if I have a finite sample, I can now do a calculation of what is the degeneracy of each of the Landau levels. So again, we have a spectrum of Landau levels. Each Landau level is degenerate, and I want to compute the degeneracy. Degeneracy is just how many electrons can fit into one Landau level, okay? And you have to do the calculation for a finite system, otherwise you get infinity. Okay, so let's do the calculation and you'll see something very interesting coming out of it, which at least gives a hint about the origin of the quantum Hall effect, although not the explanation, but it will give a hint. Okay, so how shall we? So why do we have here a finite degeneracy? Because we have a finite width in the y direction. Let me try actually the laser pointer. It's this. Sorry. This, yeah, somehow. Oh, just have to press it. You don't see it on the screen. Okay, so no use. Sorry. Okay, so okay, but actually, let me maybe go to, sorry. But then the recording will not work. Okay. Let's see. So how many particles, how many electrons can we fit in the system? We have to look what is the distance between two guiding centers. So we have different YKs, right? And if Ly is finite, the YKs have to be an integer multiple of something, right? They are determined by the boundary conditions. They're quantized. So inside a length of Ly, I can fit some number of different guiding centers, and that's going to be the degeneracy. Okay, so there is a fundamental delta YK is going to be LB squared times delta K. Delta K is the difference between two values of K that are allowed. What is delta K? It's 2 pi divided by Ly, right? I'm assuming here periodic boundary conditions for simplicity. So this is the quantization of values of K, and you just take them and multiply by LB square, and you get delta Y. Okay, so yeah.
Because we are considering symmetry in x direction.
So again, the states are completely extended in the x direction.
Yes, ma'am.
Therefore, there's nothing. So actually, the value of Lx is also important. We'll come to it. But first, now I'm looking at what limits my number of states is how many guiding centers I can fit inside a length of Ly. Okay? Okay, because the guiding centers are just an integer multiple of something, and they cannot go outside of the system, right? Okay, so what is the degeneracy? Sorry, yeah. Sorry, I made a mistake here. Sorry. Now okay, sorry about that. That was a mistake. Yeah, of course. K. So again, K is a momentum in the x direction. That's why it's quantized in the x direction. Okay, but the degeneracy is coming from the fact that the delta y, that the yk has to fit inside Ly. Okay, so delta k is 2 pi over Lx, and the degeneracy, let me denote it by B. What is it? It's just Ly divided by delta yk, right? Just how many different guiding centers are allowed in the system. Okay, so actually, thank you for alerting me that I made a mistake. Okay, so let's see what we get. I'm now plugging in the expression. It's Ly divided by delta y. Delta y is 2 pi over Lx times Lb square. This is in the denominator. And Lb square is related to the magnetic field. There's a formula that I'll write down in a minute. But let's see what we have in the expression now. This thing is Lx times Ly is the area of the system, right? So we get the area of the system divided by 2 pi, and now LB square is H bar C divided by E B. Okay? Okay, let's rewrite it a little more nicely. What is this? E over 2 pi H bar is just H times C. That's the, let me go back, the flux number. That's the flux quantum, okay? And what we have in the denominator we have the flux quantum. What we have in the numerator is the area of the system times magnetic field, which is the flux, just the total flux in the system, okay? So this is the answer, very simple. What is the degeneracy of a Landau level? You can fit as many electrons as there are flux quanta. If you think of the flux as something that is really, you know, like in the elementary schools, that you have a field of arrows, okay, these are the flux quanta. So the number of flux quanta determines how many electrons you can fit in a Landau level, and a full Landau level is one that has exactly 1 electron per flux quanta, which is, if we relate it to the concept of a filling factor, it's filling factor 1, okay? So, okay, so a full Landau level is a state that, that has exactly the number of electrons that would fit into an integer filling, and if we fill n Landau levels, we have some higher integer, but they're all integers, okay? So it suggests that this has something to do with the quantum Hall effect, but it doesn't explain what we see, right? It doesn't explain any of the observation. Why? Because what the observation is a transport experiment. You put current and you measure voltage. Why does it behave like that? You cannot get it just from looking at the spectrum and the wave function. You cannot get the answer. You have to think of a measurement to understand what it does. Moreover, there is something very puzzling here on the first sight, and this is, if I'm looking at the spectrum, let's think of K. K is a momentum, right? It's a momentum quantum number, and energy as a function of K suggests that it's a band. It's a band, like in solid state. But it's a flat band, and typically the Fermi energy will lie somewhere in the middle, right? If I'm just arbitrarily choosing my density of electrons, I have some Fermi energy. It lies somewhere in between. Typically, it will be in between, in a gap between 2 bands, right? So in solid state, if we see such a band structure, what are the conduction properties of this material? We expect them to be, expect it to be an insulator, right? Because if you try to pass current, the Fermi exclusion doesn't allow you to pass any current. You have to jump across a huge energy gap to get some current. So it will be an insulator. But I just tell you, not only it's not an insulator, this quantum Hall state has 0 resistance. So how can it be? Of course, it has to do with the fact that conductivity is a tensor. And indeed, sigma xx is going to be 0. But sigma xy, which is the whole conductance, is not 0 and is quantized. Okay? And therefore, by the way, I hope it's clear that if you have a state with sigma xx equals 0 and sigma xy equals something, something non-zero, the moment we'll soon show that it's quantized, but let's just assume that it's finite. What is going to be rho xx, rxx, okay? You just invert the tensor and you find also 0. Okay? So it's possible to have rxx and sigma xx 0, but the most astonishing thing is that sigma xy is not 0, and it's not 0 because there is a magnetic field, but not only it's not 0, it's going to be quantized. And in order to see that it's quantized, this is not something you can get from drawing the spectrum, right? Because it doesn't tell you anything. In fact, you don't understand why you can pass current at all, because if I just look at this spectrum and believe that it's true, you know, ideally, then what is the velocity of electrons in the Landau levels? According to this picture, velocity is a group velocity. It's the epsilon decay. It's 0. So how can you pass current? Okay? So in order to understand, to get the phenomena of the Hall effect, you need to think of a measurement. It's not enough to write a Hamiltonian and solve it. You need to think of a measurement. Okay? Okay, so let's go to, so what I'm going now to draw. Actually, what I'm going to show you that you can get the quantum Hall effect in many ways, and you always get the same result. Okay? That suggests that the effect is very robust. Okay? It is invariant under a lot of changes you can make in your system, including disorder potential, of course up to some limit. But also I can suggest very different measurement geometries, and you always get the same answer. Okay? So today we'll only do one of them, but let me first introduce I'll introduce the measurement geometries. Okay, so geometries. Okay. Let me start with the first one, is the geometry that is really the experiment that usually the experimentalists are following. It's a Hall bar. A Hall bar is a piece of conductor where you connect contacts, and in order to measure a Hall effect, you need to have 4 contacts. Okay, and you use 2 of them for current and possibly for longitudinal voltage, and the other 2 for the Hall voltage. Okay, so one geometry is that you connect a current source, and measure voltage, and the current is in the x direction, and the voltage is in the y direction. Okay, so this will be, so this is one geometry. You pass current, measure voltage. This is what experimentalists do in the lab, in a standard, the most standard experiment of this type, okay? Now, there is another geometry that is trivially related to it, and let me call it B. This is geometry B. It's the same whole bar, but you just interchange the role of voltage and current. You put a voltmeter in one direction and you measure the current in the transverse direction, okay? That's B. Okay, so this is Vy and Ix. Okay, so basically it's the same. It turns out the second geometry is less natural experimentally, but it's easier to treat theoretically, okay? But I want now to introduce two other geometries, and these are the ones, or one of them I'm going to start with. Let me call it C. And this is a so-called Corbino disk. It's a two-dimensional, it's annulus basically, with a hole in the middle. And you can make contacts to it and pass current through it. So you can pass current, but the way you are actually inducing a voltage is not with a voltmeter. You don't have separate contacts, but what you have is a time-dependent, sorry. Let me call it phi twiddle. You pass a time-dependent flux, okay? So let it be C times V times time. T is time here, okay? And d phi dt will give you a voltage, okay? So a time-dependent flux creates a voltage, or not a voltage really, it will create an electromotive force. So there will be an electric field in this direction, and it will induce, if there is a Hall effect, the magnetic field, by the way, I didn't explicitly draw it, but magnetic field here, B, is perpendicular to the annulus, okay? It's a two-dimensional ring, and there will be, if there is a Hall effect, then there will be current in the perpendicular direction. IY, okay? So the current will flow radially, and it will be collected by the contacts and flow in a circuit, okay? That's a Corbino, that's another experimental, very useful tool. And there are various differences between this and the whole bar, but it's a bit complicated to analyze theoretically, because here the geometry is radial and the current density is not a constant. So let me now draw geometry D. Geometry D is something you cannot realize in an experiment, but I'm claiming that it's completely equivalent to the Corbino. What is it? You take this annulus and you now squeeze it and make it into a cylinder, okay? But you maintain the magnetic field perpendicularly to the area. Of course, such a magnetic field in nature cannot be realized because it has a finite divergence. But for theory, it's very useful to draw it like that. So let me draw a cylinder. So what is a cylinder? It's just a strip, this whole bar that is closed. It has periodic boundary conditions in one direction. And now I'm adding this time-dependent flux, just like in the Corbino, which creates an electric field in the EY direction. The magnetic field is sticking out of the system in an unnatural way, but it is, again, for a big enough system, the fact that it looks like this is that you cannot really realize it is completely equivalent to the Corbino. And now what you are doing with this system, you're connecting contacts here, and current can flow IY in the Y direction, okay? Okay, so this is connected to the cylinder from the two sides. The cylinder has finite edges, but in the X direction, it has periodic boundary conditions, okay?
But if you take Corbin, they can do it with both of these are the same kind of cylinder.
Sorry. Thanks for, yeah, there's another mistake, just because I spent too much time on the drawing. There's another mistake, you are completely right. That's not the right, okay, yeah. The current actually goes, so you have to put contact one inside in the hole and the other side right, okay? That's the correct connection, and with the cylinder, it's much simpler to see it, okay? Yeah, sorry, my mistake. So this is, in the Corbino, the current flows radially, okay? Okay, so I think I can finish this we still have 3/4 of an hour. Do we need a break? Because, okay, because this is, now I'm going to really prove to you that you're going to get a quantized conductance, and we'll do it on the Corbino, not on the cylinder, okay? Okay. Yeah, so as I said, this is not a realistic geometry. It's useful for a thought experiment, but it is it's equivalent. It's equivalent to the Corbino. It's just
if the gauge is predicated
no. So I'm saying, yeah. Yeah, so you're right. I cannot create such a magnetic field in the lab, but what it is just, if you like, imagine that you have a very big annulus, very big and thin, okay? So the circumference of the edges is almost the same. In that limit, the fact that the current flows radially is not so significant. So in a sense, the cylinder is a Corbino in the limit of very big and thin, okay? So it is equivalent, okay? It's equivalent provided that you can somehow engineer the magnetic field, and your electron system just lives in two dimensions, so it doesn't know about the three-dimensional world, okay? That's the thought about it, okay?
You can just put like imagine that you have like some magnetic south poles, you put it along the line of the cylinder, like the central axis of the cylinder. right?
Yeah, I mean, yeah, right.
But since you're solving the problem on the surface of the cylinder, divergence of B is always zero there. It's non-zero
Right.
only along the axis. On the surface of the cylinder is zero.
That's right. That's right. That's right. That's right. And the only reason I'm using the cylinder, not the disk, is because I want to avoid non-uniform current density and complicated stuff, and use Cartesian coordinates for my wave functions, just the same Hamiltonian that I used before, but place it on this geometry. Okay? Yeah.
Ma'am, the kx is already quantized along the x direction. So it's like you are already considering the periodic boundary condition. So
yeah.
so
I'm
able
getting
to understand
okay.
this geometry.
Okay, so this is actually exactly the crux of the matter, because you're right that if I'm just looking at the system at equilibrium, the way I wrote it in my Hamiltonian, the wave function satisfies periodic boundary condition, and you have certain values for kx, but here you have a flux in the middle, and the flux in the middle changes your Hamiltonian. Okay, so let's see exactly what it does. That's exactly where the current will come from. Okay. Okay. So I have the same Hamiltonian of before, but there is one ingredient that I'm adding. Actually, let me put it down. There's one ingredient that I'm adding. There is a flux that you can think of this flux phi tilde as an integral of some additional gauge potential. Okay, so there's some
B dot D.
There's some additional gauge potential. I call it A twiddle. Okay, it's not the same one that introduces the magnetic field, and that's what is responsible for the flux phi tilde. Okay,
Is this flux is not originating from that B magnetic field?
No, that's exactly the thing. It's not. So there is a constant magnetic field, uniform magnetic field. That's static. Okay, on top of that, you have an electric circuit where you have some additional coil, or you have some electric circuit that introduces a time-dependent flux. Okay, so it's an independent additional gauge field. Okay, and it plays the role of a driving force. It's like, instead of putting a battery, okay, you're using this. Okay, but if I want to put it back into my quantum mechanical problem, there is another gauge field, and I have to add it to the Hamiltonian in exactly the same way as I usually do. I take my P and I now change it to P minus E over C A twiddle, right? So now, what is the direction of this A? So the direction of A here, sorry, okay, so what is the direction of A twiddle? It's actually in the x direction, right? So this line integral is around the circumference of the cylinder. Okay, so this A twiddle is in the x direction, and therefore it shifts the values of px. Yeah? Was there's a question? Okay. Okay, so px is going to be shifted into px minus E over C A twiddle. Okay. And now we have a slightly more complicated problem than what we had before, because before Px was just free momentum. It was quantized in multiples of 2 pi over Lx, and okay. But now I have this flux that now changes also Px, okay? So I want to somehow modify my wave function to correct for it. How do you do it? How do you cancel this additional flux? You are making a gauge transformation on the wave function, which amounts to changing it by a phase. So psi of the before now goes to psi times e to the phi of x, where phi of x is now a phase. And if you are now applying the, now looking at the momentum operator you apply it now on the wave function psi. Let me call this psi twiddle. You are going to get two corrections that you want to cancel each other, okay? So one is coming from the extra flux and one from the additional phase. And it looks like this. So from the phase factor, you get a correction d phi dx minus E over C A twiddle. And the way we determine our gauge transformation is we want these two terms to cancel. Okay? Okay, that's the idea. So you correct for the wave function such that it compensates for the addition of the flux. And the solution for that is that I get an expression for this phase, phi of x. It's going to be, I'm just writing the results, but it's easy to get it from here. It's an integral okay? That's what it is. Okay, let me actually call this maybe dl. Okay, so A tilde is actually along the x direction and dl goes around the cylinder, okay? So this is the phase. And if I'm now looking at my, let's write the wave function with the gauge transformation, it's given by e to the I phi times the same factor that we had before, e to the I kx. Okay, that's the new wave function. But now this new wave function has to obey periodic boundary conditions once again, right? It still has to obey periodic boundary conditions, but it has the extra phase. So the quantization condition will no longer be that k is an integer multiple of 2 pi over Lx. There will be a correction, okay? So let's see what it gives. Okay, so I'm using periodic boundary condition in the x direction, okay? Because again, there's a cylinder. I lost the drawing, but this is Ly, and this is x, and this is y is the perpendicular direction. So there are periodic boundary conditions, and if you plug this in, let me just write down the result. You get a new quantization condition for k. The values of k are 2 pi over Lx, but they're not just integer multiples, but they're going to be integer minus phi tilde over phi naught. Okay? How do I see it? Yeah.
It looks like there is a physical difference between these two situations. Right? It's not just gauge transformations of each other. Like one has physical electric field along the circle.
Of course.
How can you relate the two just via gauge transformation? I mean, if two wave functions are related by gauge transformations, they are supposed to be physically equivalent.
So yeah, no. So the correct statement is that the wave function has, once you apply a flux,
Yes.
it introduces a shift of the phase. That's what it does. Okay, I mean the original wave function will no longer be a solution. Okay.
The thing where I was confused about that, you're obtaining a solution in a different physical problem with just a gauge transformation, which looks a bit odd.
Okay, so it's not a gauge transformation that so how to put it? It's not a gauge transformation that solves the same problem. Okay, you're right. You actually have a physical additional field.
Right.
So this field forces the wave function to develop. This is what I wrote here as psi. It's the correct wave function. Okay, that's the correct wave function.
You are adiabatically changing the Hamiltonian, right? You are adiabatically changing the...
I'm changing the Hamiltonian. Yeah, the Hamiltonian is changed because px is shifted. Okay?
Okay, I'll think about it. Yes.
Okay? Yeah?
If the system already have a gauge transformation from the vector potential, initially it has no vector potential, like EA. From original Hamiltonian already has a vector potential.
No, it has a vector potential from the uniform magnetic field. That we already took into account.
So why don't we add the extra flux in that wave function? It will give us same result.
No, it's an additional vector potential, right? It's an additional vector potential, and the wave function is the same wave function of before times a new phase factor that must be there to solve the new Hamiltonian. Okay? Okay, so the phi tilde is actually changing the Hamiltonian. Okay? And I'm assuming that it changes it adiabatically. So the fact that it's dependent on time will assume that time is just a parameter. Okay? So once again, it's a new Hamiltonian. Okay? Because there is an additional field. The additional field is introduced just to realize a measurement, but it changes the wave function. And it changes it in such a way that the allowed values of k are shifting. Okay?
Okay.
All right? So, yeah, I mean, you just need to do the algebra, but that's yeah. Okay? Okay, so Good. So we have now we have a problem that is similar to before, but now we have a new quantization condition for k, and here n again is an integer, capital N. Okay. All right. So, yeah. All right. So, okay. Now we recall. So I did this exercise assuming that phi tilde is some additional gauge field, and I ignored the fact that it's dependent on time. But now I want to assume that it grows linearly with time. And let me write it again. It grows like some factor. Okay, c is just the velocity of light again. V is something that has units of voltage. In fact, it's the electromotive force. Okay. And it's linearly growing with time, and let's assume that it's changing with time very slowly, so I can treat time as a parameter. This is an adiabatic approximation, okay? I just treat time as a parameter, and what I want to show now is if you look at your allowed values of k, remember that k, the quantization of momentum in x is also a quantization of guiding center in the y direction, okay? So if the kn's are shifted, the yk are also shifted, okay? Now let's imagine that there is during a period of time, an infinitesimal period of time that I call dt, I change the flux phi tilde by one flux quantum, okay? So, during phi tilde changes by exactly one flux quantum, okay? What happens to the kn's during this time dt? What happens is that kn changes into kn minus 1, right? Because I changed phi tilde by one flux quantum, n was shifted into n minus 1, okay? So let's look at our quantum states. We have our guiding centers that are proportional to this k, right? So I'm writing this is again yk is up to a constant proportional to k. So if the values of the allowed k are changing, the guiding centers are shifting one to the other, n to n minus 1, n minus 1 to n minus 2, and so on. So what happens during this infinitesimal time dt? What I have is a shift of states, okay? I'm shifting one electron down this ladder of states, and the last electron will flow out of the system, okay? So during a period of time dt, exactly one charge of an electron is pushed out of the system, okay? So what happens is that we get a current. We get a current. This current is in the y direction, right? Because it flows. So if this shift of state happens, I'm if I have my contacts here and here, this goes out to the circuit, okay? So IY, the current in the Y direction of the cylinder equals to the charge in a unit time dt. The charge is just the charge of one electron. Okay, so I get the current of E over dt. Okay, but another thing that happens during the same infinitesimal time dt is that the flux is changed by phi naught, and therefore I have electromotive force V equals 1 over C. This is the expression, right? Because I changed the flux by a little bit, d phi twiddle, during the same time period dt, but d phi twiddle is just phi naught, right? It's exactly this thing. It's the infinitesimal change of flux. Okay, and this voltage is actually the voltage that I develop in the x direction, right? Right, it's the electromotive force in the x direction. So let me actually call it Vx. And now let's do the calculation. I have a voltage in the x direction that comes from electromotive force, not from a battery. And I induce a current. And I induce a current exactly because of this shift of quantum states. And therefore, and the current is in the y direction. So there is a whole conductivity, sigma xy, which by definition is just Ix divided by V of y. Okay? Now let's plug it in and see what we get. Sorry, that's the current is E over dt. The voltage is phi naught. Sorry. Sorry, yeah. Thanks for being alert. Y Vx, right, okay? This is what it is, up to a factor of C, which I put here, okay, in my units. Okay, and now dt cancels. This was just for a pedagogical thing. It's an arbitrary time interval. So what did we get? Phi naught is hc over E, and what you get from here is exactly E squared over H. Okay? So let me summarize. What is the exercise that we did here? Apart from, okay, deforming a Corbino disk and magnetic field and so on, we apply a voltage and measure current. This is what we always do in transport, but here we apply the voltage by a time-dependent flux. A time-dependent flux creates an electromotive force in the x direction in the circumference of a cylinder. It shifts the quantum states, but the fact that momentum states in x determined position in Y causes the quantum states to have a shift in the Y direction, okay? And therefore, it doesn't matter what is the rate at which you do it, because you see it cancels, you get a quantized Hall conductance of exactly 1 E square over H, okay? And that's the integer effect, because all I said assumed that you're looking at a single Landau level, okay? In a single Landau level, all these states corresponds to a single Landau level. If I have more than one Landau level field, they just add up, right? Because they're independent levels, all of them are exactly identical, all of them have the same degeneracy, the same type of states, except that they have a higher energy, that's all. But their contribution, if they're n Landau level field, you're going to get sigma xy is just n times E square over H, okay? So it's quantized. Notice that this was done on a idealistic system that has a cylinder geometry, and you can ask what happens if I now have rough edges and I have all sorts of, yeah, you wanted to ask? Yeah?
Original problem, if you just put the voltage equal to some time derivative of some vector potential,
Okay.
so won't you get the same answer?
Sorry, maybe you can use it like?
The voltage can, if in the original problem, you started with a geometry, you just equate the voltage to a time derivative of your vector potential A.
Yeah.
And won't you get the same? It's the same.
But that's what I've done here.
So it's the same thing.
Yeah.
Exactly,
Yeah.
right.
Right.
So putting a gate, so that Vy you'll just put as a gate, right? That's all you've done.
So this flux phi tilde is an addition.
So it just, yeah.
It's an addition of, actually, well, always when you create an electric field, you are putting some electromagnetic force in one way or another, okay? You can do it by applying, by connecting a battery. This is what we'll do tomorrow, okay? So tomorrow, actually, I'm going to show you another way to get a quantum Hall effect that corresponds to the Hall bar. And the experiment looks very different. It's a different setup, but the result will be the same. And in that picture, actually, just a minute, the advantage of the Hall bar calculation is it will be easier to see how robust is the effect, okay? Because here, okay, this is a bit of a fancy geometry, but I'll show you tomorrow how to do it in the Hall bar, and yeah, okay. And the thing that we avoided in this calculation is, apart from the boundary condition, we don't have any effect, any physical effect of the edge, okay? And therefore, we could use wave functions that are known exactly. They are exactly the harmonic oscillator, and in that sense, it's very idealistic, okay? When you have edges, it looks on the face of it that it's a more complicated problem, but then we'll show that nevertheless, it magically always gives you the same result, okay? There was another question? Yeah.
So, obviously the pendulum the only paradox flux is changing, or the functional form of how phi changes also matters.
Okay, so I'm assuming, okay, that's a good question. I'm assuming a DC voltage, okay? So if you're considering a finite frequency, if you have an AC voltage, of course, in the quantum Hall effect, there will be also an effect of that, but that's another complication that I want to avoid, because there will be the external frequency and the cyclotron frequency, or if you consider a general time-dependent flux, it will give you some time-dependent voltage, right?
It won't be quantized. Like here we are getting sigma epsilon.
Right. It will now become a non-equilibrium problem. So it will become inherently time-dependent. Okay. In my calculation, actually, I'm assuming linear response. Okay, linear response, and that I have actually a DC voltage and DC current. And one way of getting a DC voltage is if I have a flux, time-dependent flux, but if it changes linearly. Okay?
What economic assumptions systems?
Good question. So actually, in this calculation, this is an ideal electron gas, and there's no sense of measuring. Okay, you could connect a voltmeter to the x direction, like putting another. I could put 2 electrodes here and measure voltage. I could, but my calculation actually assumed that k is a good quantum number, so I have a free wave in the x direction, and therefore it's ballistic. Okay. Now, what you are asking is, okay, what if I now introduce an impurity? Resistance comes from backscattering. Okay. So to analyze that, it will be much easier to do in the whole bar geometry, because there you actually follow the velocity of particles, if you like, of individual electrons, and we are going to see that they are ballistic. And even if you put impurities, the impurities are ignored. Okay, unless they are very, very strong. But if you just make geometric deformation of the whole bar, we'll discuss all that tomorrow. Okay, I'm just saying it as a teaser. But then we'll be able to explain both phenomena, both the fact that it's ballistic. Okay, there's no resistance, no longitudinal resistance. And there is a quantized conductance, and we'll also see how to generalize it to the fractional effect. Okay, and that can be done also. Using the whole bar geometry. Okay, so this will be the lecture of tomorrow. I think now it's a good time to stop, and now I'm thinking maybe tomorrow I'll use the regular board. I think I'll feel more comfortable. What do you think? Right? I think this somehow, yeah.
But this looks quite nice, actually. Lighting and photo, video recording.
Yeah, in fact, I actually have some PDF files of the lecture notes for my iPad, which look nicer. So as a backup, I can supplement them. Okay, but maybe I'll use the board just for me to feel more comfortable, and Okay, so thank you for the attention.